الله أكبر. Are you? لا إله إلا الله. Calm down.
The first strata that formed an aerially extensive continuous sedimentary body over Libya are represented by the Hisana Formation.
Well, actually the Hisana Formation is late Cambrian. So whole this section is characteristic, means siliciclastic with shelly stuff. So all this formation deposit as integration between fluvial to shallow marine area.
If you like layer cake stratigraphy, the Upper Cambrian is for you. A monotonous pile of sand, pinching and swelling across the region. In some places, the Hisana is 1 kilometer thick. For example, at the eastern Morzuk margin in the Dor El Gusa area and in the northern Kufra in wells A1 and B1 NC43. In other places, the Hisana is more in the range of 100 to 400 meters, such as at the western and northern Morzuk margins. Southern Libya at that time lay in high southern latitudes. The climate was moderate because polar ice caps were absent. The onset of Hisana sand deposition was triggered by a rise in oistatic sea level, creating new accommodation space that could now be infilled. The sea had flooded the western Morzuk and eastern Kufra basin areas. The present-day Tibesti and its flanks, however, stuck out of the sea and formed a large peninsula. Large networks of rivers carried their sediment load into the southern Libyan area. Debris collected and transported over thousands of kilometers from the vast Gondwanan hinterland. Only the toughest minerals survived this arduous journey. What came out of the Hisana rivers was mostly quartz. Seasoned grains and pebbles, mostly well-rounded. More fragile minerals didn't quite make it so far and fell apart already in the early stages of their long journey. It is these Gondwanan quartz grains that are the primary building blocks of the North African Paleozoic basin fill. Not only during Cambrian times, but during various episodes during the Phanerozoic. Grains that became trapped in southern Libya on the gradually subsiding shelf. Some of the sands already became deposited in the Tibesti fluvial basin, forming monotonous stacks of planar and trough crossbeds. There was no vegetation yet to stabilize riverbeds. Paleo currents flowed generally towards the northwest, a pattern that hardly changed in the following 400 million years. Much of the Hisana sand was eventually dumped into the Shelful Sea. A very shallow marine deltaic depositional environment, probably with large tidal areas. The sediments are dominated by planar and trough crossbeds, formed by downstream and lateral accretion in channels and bars. The sea floor was nicely decorated with wave and current ripples. Channels were cut by fast-flowing currents. For a long time, this is what essentially happened in southern Libya. And it also didn't change very much when the Ordovician finally arrived. The shelfal sea grew a bit, but apart from that, the depositional setup continued to exist. The constant rhythms of nature had a firm grip on southern Libya. Tides came and went. After a day came a night, and then another day. Earth history consists of long periods of boredom and short periods of excitement. But excitement was still many millions of years away at this point in time. During the early and mid-Ordovician, the Az-Shabiyat and Hawaz formations were deposited, sandstone-dominated units with a few finer-grained interbeds. The most prominent inhabitant of the intertidal to shallow subtidal zones at that time was a worm. In a way, it was similar to the modern wadden worm, Arenicola marina, at the North Sea coast. Restlessly, Arenicola churns through the top 20 centimeters of sediment, looking for organic food particles. Every 45 minutes, the worm comes to the sediment surface and excretes unwanted sand. Hidden underneath the pile of sand is the worm's tube. The Ordovician worm built very similar vertical burrows. If the burrows are spaced very closely, the sedimentary fabric is also called pipe rock. But unlike Arenicola marina, that had to churn his way through the sediment, the Ordovician worm sat in his burrow and waited for the food to come to him. His helpers were the waves and currents that carried his food in suspension. The Scolissos worm liked high-energy conditions. Scolissus trace fossils occur in various stratigraphic intervals of the marine Paleozoic of southern Libya, but they're most common in parts of the early to mid-Ordovician Hawaz and Az-Shabiyat formations. Here, the pipe rock can become several tens of meters thick and makes a good local stratigraphic marker. The general tectonic stability of the shelf across North Africa through this period resulted in the deposition of broadly similar Cambrian and Ordovician successions across the entire region. Nevertheless, on a local scale, tectonic movements have been certainly active. In Dor El Gusa, at the eastern Murzuk margin, the Hisana and Hawaz contact is marked by a distinct angular unconformity. Intraplate uplift must have occurred here during the late Cambrian or early Ordovician, but has not been reported from other parts of southern Libya. Despite its good reservoir qualities, the Hisana is most probably of little relevance to petroleum exploration in Murzuk and Kufra. In most cases, the unit may be too far away from the Silurian source rock, and vertical throws along steep faults are often too small to juxtapose Cambrian sands and Silurian source. But most importantly, there's a serious sealing issue in the Hisana. Although shales do partly occur within the unit, regional seals for the Cambrian appear to be absent in southern Libya. The story is very different for the Hawaz. The mid-Ordovician sands are a proven reservoir in some of the Repsol Murzuc fields. As we'll see later, Ordovician erosion has brought some of the Hawaz in direct contact with the Silurian source, opening up a fascinating stratigraphic play type. When looking at well logs, isopac maps and seismic lines, one tends to forget that there are real rocks behind the data. Rocks that could be touched, studied and followed at outcrop over long distances. But what's the role of traditional fieldwork in a digital world like ours? Why bother stepping out of the air-conditioned office when you can overlay hundreds of fanciful maps and detailed data sets on a geographic information system with a few mouse clicks?
Of course, today in exploration we have a lot of technology, some very good technological tools, very high quality seismic data, very good modeling packages. But fundamentally the data that we use for exploration, certainly in areas like the Sahara and southern Libya, still relies fundamentally on the outcrop geology. It's the outcrops that we need to go to understand the facies distribution, the thickness of the sedimentary sections, the distribution of the source rocks, the periods of uplift and tectonic activity. These are absolutely fundamental to our understanding.
You know that what we have in the surface reflects exactly what we have in the subsurface. So understanding the surface geology is a key issue. No matter what you do in exploration, no matter how many wells you drilled, you cannot know exactly everything unless you know the surface geology, because that's the nice thing about geology. There you can see everything. You have a scale of things.
There are so many models that are in 3 dimensions. You can see them, you can walk in the reservoir, you can see the relationship between the reservoir and the source rock. They are right there. All you have to do is just have to really compare the outcrop with the subsurface.
I have a good example from Egypt. In Egypt, an oil company wanted to drill it's the southern Gulf of Suez, northern Red Sea area for oil in Cretaceous sands. And they found no Cretaceous sands, consequently they found no oil. But if they had listened to field geologists, they could have learned that the Cretaceous sands pinch out much farther north than they expected. But same thing in Murzuc Basin, I think. If you do not understand the facies changes within the different formations and especially their directions, you have a hard time to interpret your seismic, I think, or to interpret your drilling results. And let's face it, fieldwork is cheap. So you always can learn, you can gain information which you can use in drilling.
The Ordovician years rolled by, with the sea comfortably ruling over southern Libya. A greenhouse climate, warm and cosy, which continued right through the Silurian and Devonian. If there wasn't this short, peculiar interlude in Libya's geological history. For a short while during the late Ordovician, strange things happened. Things that struck most of Gondwana by complete surprise. It was suddenly getting cold, seriously cold. the trilobites will not have liked it. We still don't know for sure what suddenly turned the air condition to cold and made southern Libya this giant natural fridge. Out of the blue, a giant ice cap built up over the Saharan area. The average temperature fell to -50 degrees Celsius. It's never been colder in southern Libya ever since. The following 5 million years decided the fate of the Mourzouk and Kufra basins as a petroleum province. In places, the glacial upper Ordovician sands of North Africa are full of oil or gas. Across the Sahara, at least 5 billion barrels of oil equivalent have already been found in these strata. The black gold is stored in more than 50 fields that form a broad belt stretching from central Algeria into the northern Mourzouk basin. Here in southwest Libya, at the eastern end of the belt, lie half of the discovered volumes, in the Mamouneat Formation. The main reason why on the maps today this petroleum province ends in the northern Mourzouk is that hardly anybody drilled further east.
To begin with, we certainly didn't appreciate either the complexity of the Cambrian Division stratigraphy or the changes of facies within even particular units of the stratigraphy. So certainly the reservoir, understanding the reservoir system, we thought it would be easy and not one of our problems, and it was somewhat harder than we anticipated.
The Mamouneat Formation, because it is a glaciogenic unit, is very complex. And one of the key issues that we have in terms of field development very often is the continuity of the reservoirs. Like all glacial systems, there is a great deal of heterogeneity in the system. And it's very difficult on the seismic data to be able to determine the individual facies.
And if we see most of these dry reservoirs due to the quality of the reservoir, I know that is not easy to have 100% understanding of the Mamouneat reservoir. This is one of the main risks in our area.
We know a great deal more about the Mamouneat Formation than we knew maybe 10 or 15 years ago. A great deal of research work has been done, a lot of the outcrop work has been done in that period of time. So we now have a very clear understanding of the genetic relationships between the various depositional units. But at the field scale, it's still quite difficult to predict what the lateral continuity of particular reservoir sands is going to be. And careful mapping, 3D seismic is also proving the ability to improve our predictive capability. There is not a great deal of 3D seismic existing at this point in time within much of the southern Libyan area, but that will certainly form one of the keys to improving prediction in the future.
The huge Gondwana landmass lay straight over the South Pole during the late Ordovician, and the broad, uniform North African and Arabian shelf was an ideal platform to accumulate thick ice masses.
The evidence available to us from the Sahara suggests that the ice sheets were very large and continuous at their maximum extent, very much like the modern East Antarctic ice sheet.
The Antarctic ice sheet covers almost 14 million square kilometers. In East Antarctica, the ice sheet rests mostly on land, while large parts beneath the West Antarctic ice sheet would be seabed if the ice sheet were not there. On average, the modern Antarctic ice cap is 2 kilometers thick, but in places the ice column measures 4.5 kilometers. The late Ordovician ice sheet in Gondwana may not have been very different. Large areas covered by ice and great thickness means also great ice volumes. And this is the powerful control button that make glacial deposits so heterogeneous and the system so complex. A small change in climate can cause large volumes of ice to rapidly melt and raise sea level significantly. Likewise, build-up of additional volumes of ice on the ice cap extracts the water from the world's oceans and lowers the sea level. Climate, the size of the ice sheet, sea level, sedimentary facies, and Ordovician reservoir quality are intrinsically coupled. It's worth taking a closer look at where the ice sheet was and how the late Ordovician glaciation worked. The centre of the Gondwanan ice sheet lay just south of the Sahara, maybe in present-day Chad. From here, the ice flowed outward into all directions. Rocks underlying the central parts of the ice sheet were eroded and the debris transported towards the ice margins. Here, the strata was deposited. Glacial sediments from the late Ordovician are preserved across Gondwana and have been discovered so far in South America, South Africa, Saudi Arabia, Jordan, Libya, Algeria, and Morocco. Knowing where the edge of the ice sheet was at a particular time is important, because this is where sediment is freed from the ice sheet and where the most significant sedimentary facies changes occur. So where was the edge of the glacier in North Africa?
We can say that the ice sheets terminated in northwestern Morocco. Okay, where we have the chance of connecting the outcrops together in a depositional model. And they appear to have stopped there because there's a major break in bathymetry. So a big change from where you have sediments of perhaps 20 metres or so in thickness being accommodated on the shelf to a rapid increase of about 400 metres plus of sediments, of differentiated turbidites. So in that particular case, if you decompact the thickness of the Ordovician turbidites in northern Morocco, you're talking about very deep water in that part of the world. For the more prospective parts of North Africa, that's to say in central and eastern Algeria and in western Libya, the story is more complicated because the evidence for where we might find the limit of the ice sheet is now in the subsurface in the northern part of the Khadamis Basin. The further north you go in North Africa, the greater chance you have of truncation, tectonic truncation by the so-called Hisana Unconformity. So it's an open question at the moment.
The outward movement of ice within an ice sheet is concentrated in so-called ice streams. Most of the ice leaving the ice sheet passes through these large flow systems, which can be hundreds of kilometers long. Some ice streams flow at speeds of over 1,000 meters per year. In between the ice streams are zones of significantly slower moving ice. The interstream areas that in modern Antarctica account for 90% of the ice volume. Here, flow velocities rarely exceed a few meters per year.
We now know, based on a combination of fieldwork and the analysis of satellite imagery, that a large and continuous ice stream, up to 50 kilometres wide, was present in western Libya and eastern Algeria, and that this ice stream probably extended towards what is now the southern Aleesi Basin. So based on this finding, and knowing what we do about modern ice sheets, we would have expected similar ice streams to have been distributed unevenly over the North African area during the late Ordovician glaciation. So it's likely that really at the ice maximum, when the late Ordovician ice sheets were at their largest, the region was divided into areas characterised by very fast-flowing ice, these ice streams, separated by slower-moving ice, interstream areas.
The ice streams were most healthy during peak glaciation times. Ice was constantly added to the ice sheet, and a steady ice flow developed, fueled by gravity. Dragging ice at the base of the stream carved huge valleys. At this stage, meltwater was not involved. Things changed completely during phases of rising temperatures. The ice stream movement stagnated. Parts of the ice began to melt. Huge amounts of meltwater were suddenly released and flowed within and beneath the ice towards the glacier's edges. Networks of tunnels developed, cutting deeply into the substrate. Compared to the ice streams, these channels were significantly smaller, but still sizable structures.
One of the most common features of the Ordovician glacial depositional system is the prevalence of large paleo valley incisions. And the paleo valleys themselves are of the order of 100 to 600 metres deep in some cases, generally between 4 and 6 kilometres wide. And particularly on the Gargaf Arch, in the northern flanks of the Mazuk Basin, we can see at least 3 generations of cross-cutting paleo valleys like this, suggesting that we have at least 3 phases, in Libya at least, of ice sheet retreat.
So the main agents of erosion change during the course of a glacial cycle. Ice erosion by ice streams during peak glaciation times, and meltwater erosion of smaller tunnel valleys during glacial retreat phases. The different origin of these two valley types means that also the sedimentary infill history will differ, and with this, the reservoir characteristics. Distinguishing these features on seismic and in outcrop is therefore essential. In some areas today, we find ice stream valleys with tunnel valleys superimposed.
And sure enough, we see big basins that are carved by the ice streams, and within those basins we see the tunnel valleys themselves. So we have to think of incisions on 2 orders of magnitude, if you like. The tunnel valleys, 100 metres or so in depth, a few kilometres wide, sitting within the larger scale fairways.
Let's concentrate on the tunnel valleys for a moment. Why should we bother so much about these?
Tunnel valleys are a very interesting feature of the entire glacial depositional system that we have in southern Libya. Again, not very much was known about them until a few years ago, and we still rely very heavily on using, for example, Pleistocene analogues from northern Germany, from the northern parts of the United States, from the United Kingdom, all of which give us a very good feel for what the geometry should be within the individual tunnel valleys. They are very, very important because they often contain the best reservoir sequences, for example.
While the Pleistocene tunnel valleys make a good comparison with the Ordovician Paleo valleys, finding real modern analogues is very complicated. Antarctica would be the place to search for, but despite the global warming debate, the East Antarctic ice sheet is currently very stable and is actually even growing. Not a good place for subglacial meltwater streams to form. Seen through the explorer's eyes, there are good tunnel valleys and bad tunnel valleys, depending on their position on the shelf and their detailed infill history.
We know that the valley systems are carved in different water depths. We can see that some of the valleys appear to be filled with mud rocks that were deposited in an outer shelf environment, for example. So we have to remember that these valleys are cut in areas that are naturally prone to poor quality glacial deposits in the outer shelf region, and that some of them are cut in areas that are naturally prone to better quality rocks, that's to say in the shallow marine setting and in the braided fluvial environment. So we really have to bear those factors in mind as well.
A meltwater valley cut into the outer shelf, for example, could initially be infilled by high-energy fluvial to very shallow marine sandstones and conglomerates with good reservoir properties. As the glacier gradually retreats and sea level rises, deeper water facies get deposited, such as shales interbedded with sandy turbidites. Finally, hemipelagic finds infill the remaining accommodation space. A typical deepening and fining upward, backstepping sedimentary succession.
Thinking about the paleovalleys themselves across the region, we see a range of fills in North Africa and Arabia. On the Gargaf Arch in Libya, some of the paleovalleys contain a well-defined two-stage fill. At the base and the sides of the paleovalleys, we often see a very clean conglomeratic sandstone deposit, which we can refer to as the initial fill of the paleovalleys. This initial fill is onlapped by a secondary or main fill, which constitutes really the main thickness of the paleovalley sediments. In southern Libya, the main fills to the paleovalley consist of very well differentiated sands and mud rocks, and these contain sedimentary facies typical of underflows. So we're talking about massive beds, channelized deposits, anti-dunes, rare parallel lamination, and also some rare intraformational conglomerates. If you look at the fill to paleovalleys across the region as a whole, really the fill styles are very variable, with fluvial deposits being recognised in Mauritania and Jordan, for example, shallow marine deposits in Saudi Arabia, and relatively deep marine debris flow deposits, very muddy, in eastern Algeria in particular. In all cases, however, we note that there are really these two very well defined fill stages to the paleovalleys.
And also the shape and distribution of the Ordovician paleovalleys is variable. Sometimes they form rather isolated sinuous features, sometimes they form anastomosing interconnected networks. The complex relief and lithological heterogeneity within the tunnel valleys forms the basis for a collection of various potential stratigraphic traps.
The fill to these valleys may be highly prospective because they may contain very clean sands and also viable stratigraphic traps for oil, particularly when they're cut into mud rocks or diamictites on the shelf, or where they contain sands that are bounded by mud rocks.
And we see certainly some potential for lateral seal at the edges of the paleovalleys that would potentially give us some quite large stratigraphic traps. The topography that is associated with the glaciation is also a very important element in many of the fields that have been discovered. So we identify what are referred to as buried hills in some areas, which are the prime structuration that gives us the closure for the trapping of the hydrocarbons.
Buried hills relict pre-glacial strata, mostly Hauer sands that survived mid or late Ordovician erosion. During the Ordovician glaciation, these hills represented major highs and could not be covered by glacial deposits. Post-glacial Silurian shales provide an ideal top seal and make the buried hills a successful trap in some of the Murzuc fields.
Based on the paleo high structure, this is good traps for accumulated of the oil. If the paleo valley, so usually we don't have a good structure to accumulate the oil. So the 3D seismic, it is very clear to investigate and show all the structure traps within C115.
And in parts of the Atshan area, erosion has penetrated even deeper. Locally, the Silurian Tenizoft sits here directly on the Cambrian, and the Cambrian is full of gas.
We have A1 and C151 produce gas from Cambrian, from Hisana, as a reservoir.
The Buried Hill stratigraphic trap is a child of an erosional event that's still poorly understood. Sometimes during the mid to late Ordovician, a huge relief was cut into the pre-glacial substrate, creating an erosional surface referred to as the Taconic Unconformity. This unconformity today separates the preglacial from the glacial strata.
The origin of the taconic unconformity remains a subject of considerable controversy. There are many different views. When we look at regional cross-sections, when we look in the field, when we look at some of our regional seismic lines, it's quite clear that that unconformity cross-cuts pre-existing structures. And there is certainly some significant evidence that there is a tectonic component to it. Having said that, it has clearly also been considerably accentuated by glacial erosion associated with the northward progradation of the ice sheets, which then re-excavated much of the unconformity surface. So certainly my opinion is that it is a mixture of both a primarily tectonic unconformity that has then been extensively reworked by the ice sheets of the late Ordovician glaciation.
The assumed tectonic component must have been of intraplate character, responding to plate tectonic activities that took place several thousands of kilometers away near Morocco. During Middle Ordovician times here, the Avalonia terrain split from Gondwana and drifted off. Nevertheless, tectonic intraplate stress could have been transferred as far as southern Libya. Pan-African and younger faults could have been reactivated, with the development of transpression or transtension depending on fault orientations and geometries. Towards the beginning of the glaciation, when the sea level had already markedly dropped, rivers might have deeply cut into the uplifted blocks. When the glaciers finally arrived, ice streams and subglacial meltwater added to this complex erosional puzzle.